Thanks a lot for the introduction. I'm very excited to be here this afternoon to talk to you about my favorite research topic, which is plasma wakefield accelerators. But before I start to do that, I would like to look at the question, why are we interested in high-energy particle accelerators at all? Right? And there are many answers to that question, but from a DESY perspective, so from my home institute's perspective, there's one clear answer, because particle accelerators allow us to, or are at the heart of the machines that allow us to study the structure of matter, which is the core DESY mission. So, and this is mainly being done in two different research fields at DESY. One is particle physics. So we are using very large-scale accelerators, particle colliders, to investigate the fundamental forces and constituents of matter. And what you can see here is a simulation of the decay of a Higgs boson that was recently discovered at LHC with many scientists from the Helmholtz Association participating. And this is only made possible because we have high-energy accelerators, right? This led to a Nobel Prize in 2013. Another research field which is building on accelerators as the main infrastructure is photon science, right? And in particular, synchrotron photon sources, for example, free electron lasers, allow us to look at processes and dynamics of atoms and molecules. And in particular, this is a very heavy research focus at DESY, with the upcoming European XFEL installation at DESY. And what you can see here is an artist's impression of a very short, femtosecond long FEL pulse diffracting of a single molecule, of a single protein, actually, in this case. And from the diffraction pattern over here, you can learn how the molecule looks like, or the protein. And by doing this several times, you can learn about the dynamics. Of course, beyond matter, there are many more applications of accelerators, which I'm not talking about for the remainder of the presentation, but I would like to mention it. There are medical accelerators, for example, for cancer therapy, material processing, welding, food sterilization, for example, and there are other applications, for example, in energy science or also in security. Let's come back to FELs. What I show you here is a bird's eye view of the flash free electron laser, which is one of the pioneering free electron lasers in the world. It's located at DESY. It's a 315-meter long machine, and about 100 meters of this machine are consisting of acceleration modules. Right? So the accelerator is accelerating electrons to about 1 GeV energy, and if that doesn't mean anything to you, 1 GeV energy, 1 GeV energy electron is traveling at very close to the speed of light. It's very fast. The accelerator for this is, as I mentioned, quite big. What you can see here is a photo from inside the accelerator tunnel, and these big yellow modules here actually contain the acceleration modules. What not many people at DESY know is that in this building over here, we are actually currently developing our own 1 GeV accelerator on the second floor. And it looks like this. It's a plasma wakefield accelerator. What you can see here is a plasma cell in vacuum with a plasma light emission. It's only a few centimeters long, but exactly this type of accelerator with the same dimension has already delivered in the past GeV beams, so the same energy as the flash accelerator on a 100-meter scale. This was shown pretty much exactly 10 years ago by a group from Berkeley lab. And these accelerators are really small, right? I've got an accelerator module here in my hand, so you can put them in your pocket if you want. It's, of course, not the full accelerator, only the accelerator module. But this is kind of the scale difference that we're looking at. So how do these accelerators work? What we do is, from an outside perspective, we have the cell, the one you saw in the photograph, which we fill with hydrogen gas. Then we send a driver into the cell that loses its energy to drive plasma wakefields in here. What's that? I will discuss in a second. And then on the other side of the cell, we see that a depleted driver, which can either be a very high-intensity laser pulse or a high-charge density electron beam, is exiting the plasma cell, followed by which we call a witness beam, which is witnessing the electric fields inside these structures and is being accelerated to GeV energies. So a plasma, as we've learned earlier, is nothing else essentially than a soup of ionization fragments. So in the case of a hydrogen plasma, this is what we're using here, it's a soup of electrons and protons. And for understanding what's happening in these plasma wakefield accelerators, we can consider the proton part of the plasma as immobile, right? They are much heavier than electrons. They move on much slower time scales, so they are essentially immobile for the process of wakefield acceleration. We then send our very intense driver into this plasma, so it can be a high-intensity laser pulse, as I mentioned, and this laser pulse, by means of its photon pressure, its light pressure, is acting as an electron snowplow. So it drives through the plasma and pushes the electrons out of its way. Remember, the protons, they stay immobile, so there is a large, let's say there's a cavity of many protons and very few electrons behind this driver. So driver is propagating from left to right in this picture, which is then pulling back the electrons that have left their original position. And this is now moving from the sketch to a full 3D computer simulation. You can actually see here the electron density inside the plasma, where a dark grayscale means high electron density, and light means very few electrons. And you can see that there's a large difference in the number of electrons here, which leads to very strong electric fields, which are pointing into the direction of the propagation of the driver. And in fact, these electric fields can be so strong, they can be on the order of 100 gigavolts per meter, which is 4 orders of magnitude beyond what you can do with conventional accelerator technology. And that's why we can build a GeV accelerator of this size compared to a 100-meter accelerator of conventional technology. Another very important and interesting property of these accelerators is the scale length. The scale of these acceleration cavities here is on the order of a few tens of micrometers. That means if we want to accelerate an electron beam in there, it has to fit in there, which automatically means it has femtosecond duration. And this is really important for applications, right? We have a GeV beam with femtosecond duration. We can use this in pump probe experiments, for example, to understand dynamics of molecules or atoms, even on femtosecond scales. Also, other beam properties of these electron beams in here that can be accelerated can be very nice, so very good transverse beam quality, high currents. So this seems to be a very interesting technique, and really the acceleration process here can be imagined as being very closely or very similar to what happens to a surfer on a large wake. So the surfer can gain the potential energy of the wake and can transform it into kinetic energy. And this is nothing else than what's happening here. The electrons are surfing this plasma wake field, so to speak. And now really the art in the field is to inject this witness beam into this wake field in a way that the electrons in there all behave in a very similar way, so that we get very nice beam properties out of this. So what we want is these 3 surfers here, right, that are all in phase and do the same thing, and not this guy over here that is completely out of phase and clearly is not in the same state as the other surfers here. So what we want is to create very well-behaved and controlled electron beams with interesting properties. My group has worked on various techniques of injecting electrons into wake fields, and I'm just showing you one example which is yielding very interesting properties for these electron beams. So what we are doing in this computer simulation that I'm going to show is that we have prepared a plasma cell very similar to the one that I've just shown you, with an additional component in the front which contains a mixture of helium and hydrogen gas. Then we send in a laser beam that creates a plasma from this gas, which is then closely followed by an electron beam, for example, from the flash accelerator. And what happens now, and you can see here a full 3-dimensional massively parallel computer simulation of this, which was run on one of Jülich's supercomputers. You can see here again the electron density in grayscale. This is the drive beam which fragments in this process. And you can see here an injected bunch that was injected because the laser beam that prepared the plasma did not ionize the helium that was mixed in this jet. But the wake fields themselves have such high field strength that they can. So they actually can release these helium electrons, which are then captured in a very small section of phase space over here. And the beam back here has extremely interesting properties. Not only that it is a 2.5 GeV after only 15 millimeters of acceleration, right? This is twice the energy that flash can achieve. It also has a very short bunch duration, so this beam is 770 attoseconds long. It has a high peak current, very nice transverse beam properties. So we are quite excited, and we would like to test this concept in the near future in one of the facilities I'm going to show you on the next slides. And now, considering that we have these tiny acceleration modules, you need to know that accelerators don't just consist of these acceleration modules. So in order to really shrink accelerators down, we also need to replace, for example, electron beam transport optics by something that is much stronger than what is available today. And that's why we are working actually on the development of plasma lenses. Right? It's not by chance that they look very similar to the acceleration modules, but we are using them in a different mode of operation. Actually, we are sending a high current discharge through the cell and drive a current of several kiloamps in the background plasma. And this current is inducing an azimuthal magnetic field that can focus down a co-propagating electron beam. And we've just performed experiments at the University of Mainz at the Mainzer Microtron Accelerator to test these cells and shown focusing gradients for the experts on the order of 760 Tesla per meter. And this technology is actually easily scalable to the kilotesla per meter range, which is more than an order of magnitude stronger than what is available today from conventional electromagnets. So, and we are hoping to continue these, or our plan is to continue these studies in the very near future in the Flash Forward facility. Flash Forward stands for Future-Oriented Wakefield Accelerator Research and Development at Flash. So this is actually an additional beamline that's currently being constructed at the Flash Accelerator. And our idea and our mission is that we demonstrate high-quality beams from a plasma wakefield accelerator as a next step to use these beams in first applications, so in photon science. And this all happens under the umbrella of a Helmholtz Virtual Institute in close collaboration with our international collaboration partners. This, by the way, is the Flash facility from the outside, and our beamline is just behind this wall. I'm not going to go into any details, so this is just a rough schematic of our beamline. The main message here is that we will start in the middle of next year with first experiments, which then run until 2020. In 2020, we will add an undulator section in the end, and hopefully utilize electron beams that we have created in here in the first 3 years to demonstrate FEL gain. And I would like, as a very last thing, I would like to take the opportunity to mention that Helmholtz and DESY are really providing a unique environment which allows for state-of-the-art research here, right? And Flash Forward is not the only project that utilizes this environment. There's another project at DESY which is called LUX for laser-driven plasma acceleration. But we were very excited about the next generation facility that would allow us to go even beyond what we are planning right now. This is the proposal for the Athena-E Helmholtz infrastructure. It's a joint proposal by 6 different Helmholtz institutes to construct a laser wakefield plasma accelerator test facility at DESY that would then do the next step and go beyond plasma wakefield accelerator science and actually build usable plasma accelerators. So, to summarize, today, accelerators are very large scale, but cutting-edge machines for photon science, high-energy physics, medical applications even. But plasma technology offers a very promising path to miniaturize these machines by 1,000-fold. And our goal is, in the next years, to go from plasma accelerator research to usable plasma accelerators. And we hope that this miniaturization of accelerators will entail a significant reduction in cost, and in turn, will also allow us to support a widespread proliferation of a compact accelerator technology, right? So that every university that wants a GeV-class electron accelerator can have one, even hospitals if they want, or also developing countries that currently cannot afford accelerator technology. And last but not least, we are hoping to create beams with new and extreme properties for example, pump-probe photon science experiments. So, in my point of view, plasmas may have a revolutionary influence on the future of accelerator applications. Thank you. Oh, I forgot. Of course, I would like to thank the people in my group and in my project and our collaboration partners.